back. It's time for some mathematics. I will discuss continuous compounding, and we want to derive the principles behind it. I start by writing down the value of a fixed income security at time t, which I denote pt. T is in our case the year, so it could be in 1 year, 2 or 3 years, and so on. Now the value of your fixed income security will depend on your principal. Yeah, I denote the principal as P0. Then of course the interest payments accrued in this time period. Now it's very common that interest is paid not once a year but several times a year. For instance, it's very common you have semi-annual interest payments. So the interest which is annualized, I denote this as R, and M is the number of times interest is paid. So M is an integer, so this goes to the power of mt. Yeah, so it depends how many times the interest is paid every year, and then of course it depends on the number of years. Now I want to explore what happens in the limit where m goes to infinity. Yeah, so the interesting question I want to ask here is what happens if m becomes very, very large. Now looking at this equation, it's not completely obvious what we should expect. Yeah, so if m becomes very, very large, this term here becomes very, very small. So this term here goes against 0 plus. Yeah, so it's still positive but becomes very, very small. Now of course here you take it to the power of m, so m obviously goes to infinity, so this term becomes obviously very, very large. Now the issue there is what is the combined effect, and that's not really that obvious. Now to explore this further, we will take the ln on both sides of this equation. Now just to refresh your mind, the ln has very nice properties which we want to exploit. So first of all, the ln function, so if you just plot the function, looks as follows. It has the value 0 at 1, so the root is at 1. It's not quite looking perfectly, but this is how it should be. And when I go closer to 0, the ln of x approaches minus infinity. And obviously it's only defined for x strictly positive. Now the ln has nice properties which we exploit. One property we exploit is the following. Ln of a times b is ln a plus ln b. Yeah, so that's useful. The other one is also useful. Ln a divided by b is ln a minus ln b. Yeah, again quite useful to know. And then finally what we also need is the ln of a to the power of b is equal to b ln a. So now we use these properties in dealing with our equation and simplifying it and making it easier to discuss the limit. So if I take the ln, I obtain the following. I get ln p equal to ln p0. And that obviously becomes a separate term, so it's plus mt, this goes front, ln, and then 1 plus r divided by m. Now this helps us a little bit, but we still are not entirely sure how this will behave, because we still have our limit inside the ln. The next thing we have to do is we have to do an approximation. And what I will now use is called the Taylor expansion or the Taylor series. which you might have covered before. Let me just start with here. I'll just write down here. So this is the Taylor expansion. Now the Taylor expansion is a very useful approximation. It works quite well in a certain proximity, shall we say. So this is an expansion which works if you look at the value of a function close to the value of say a. In our case, we will actually use the value 0. Now we already know, we discussed it here, that r divided by m will go to 0 plus. So this becomes a number very close to 0. Yeah. So what we try to approximate is basically the function value at 1, because we have here 1 plus something very close to 0. Yeah, not quite, but getting very close to 0. Okay. Now the general equation for the Taylor expansion goes as follows. So this is f of x, which I assess, so vertical line, at a certain point. So just write x equal to a. This is, or better to say, it's actually approximate. It's approximately equal to the sum of n from 0 up to infinity, f to the power of n. Now this notation means I take the function f and I apply the first, second, third derivative, assessed at the value a divided by n factorial, and then x minus a to the power of n. Yeah, so that looks quite evil, but that's the Taylor expansion. Good. Now let's work with this and apply this for our case, which is the ln of 1 plus a very small number. Now let's put in x here, just to be consistent with notation, and we actually want to take x very close to 0. Yeah, because we know that r divided by m for very large m is basically equal to 0. Yeah, what we can say is this is approximately, looking at the equation, the value of this function for x is equal to 0, which will give the ln of 1, which we know is equal to 0. Yeah, so that's the easy bit. Then we have to take the derivative of the ln of 1 plus x, which comes here as plus 1 divided by 1 plus x, which is assessed at x equal to 0. And then when I'm at n equal to 1, 1 factorial is equal to 1, so that's gone. And here we just multiply this by x. Yeah, here we are, just multiplied by x, x minus a to be precise. Yeah. And then we have here, if I take the second derivative, I would get a minus, and then because it's 2 factorial, so I would be at 1/2, and then I have 1 divided by 1 plus x to the power of 2, again assessed at x equal to 0, and then I go here to x power of 2, and then I get higher order terms. Yeah, so I just get something like x3. Yeah, so these are higher order terms. We are not massively interested what's happening there. So I can now start simplifying that. Let's simplify that. So we get here the approximately, this is simply anyway 0. When I assess this term, I end up with x, and the second term is then minus 1/2. That again becomes 1, and then x power of 2, and then we have simply higher order terms. Good. So if we look at this, and if we assume that x is actually a very, very small number, yeah, so if we look at this and assume that x is a really small number, then it's plausible to argue that what I approximate this with is roughly equal to x plus higher order terms power of 2, which are very, very small. So this is very, very small because x is very close to 0, so anything to the power of 2 or higher orders can be ignored. Yeah, so it's simply a first order expansion which we apply. So if we do that and go back into our equations, and we now move back into the equation and use what we have found. Okay, let's just do that. So I just write now ln pt is equal to the ln p0, and then we have plus mt, and this term here, the ln 1 plus rm, would simplify simply to r divided by m. Yeah, and obviously this is quite a significant way to simplify it, and you see immediately that the m would cancel in this case. Yeah, so in the limit where m is really, really large, this approximation we just did is absolutely valid to do. So in the limit, we know that the ln pt is equal to ln p0, and then in this case it simplifies to rt. Now if you look at this equation, we end of the day don't want the ln of pt, we want to know something about pt. Well, what we can do is we simply take the e function on both sides. The e function is the inverse of the ln. So that would simply cancel, so you get here pt, and then you get here the e function, so exp ln p0 plus rt, and that simplifies to p0 e to the power of rt. Yeah, and this is exactly what we want. So here we are done, and we basically now show that in terms of continuous compounding, that if m becomes very, very large, it goes to infinity, we can write the value of a fixed income security as its principal times the e function to the power of rt. Good, that's all I wanted to show. I see you in the